You probably think you know quite a bit about the periodic table, and you probably do, but there's a whole lot more information found on the periodic table that we're going to unlock a little bit of it today when we talk about trends in the periodic table. Now, if you look at the periodic table, at first glance, take away what you already know about it, but it seems like a bit of a weird thing. Why is it arranged the way it is? Why is it that many columns? Why are some of them taller than others? What's these columns doing or these rows on the bottom doing? And we're not going to get into all of that, but the reason the periodic table is structured the way it is because of the information we can get from it. So we're going to need to dig into a little bit of that today, and we won't necessarily say why it's structured exactly like this, because there's things that we don't know yet, but we'll get into at least parts of it. We're going to deal with a few particular trends, properties of atoms that are on the periodic table, and we're going to start with atomic radius. Now, this one's going to be kind of our longer one because we're going to use atomic size to help us understand some of the other things. So this one we're going to dig in a little bit deeper. Radius, how big the atom is, and think of it as a sphere, but we can draw a circle, how far away the outside electrons are from the nucleus. There's going to be a balance between different factors. Number one is the electron-electron repulsion. So the more electrons I have in there, they're repelling each other. That's going to push the atom out to be a little bit bigger. There's also the nucleus electron attraction. So the protons in the nucleus, the positive charges, they're going to be attracting those outside electrons, and that's going to be drawing the atom in. At the point where those two things balance out is where the atom is going to stop changing size. Now, within that, you get something called effective nuclear charge, and really what that means is if I've got, pick a number, 30 electrons in my nucleus, the outside atoms, did I say 30 electrons? 30 protons in my nucleus. My outside atoms are not necessarily going to feel the pull of 30 protons because of these other things, all the other electrons in between, and because of that electron-electron repulsion. Going to get into that a little bit. So effective nuclear charge is not necessarily the actual nuclear charge, but we're not really going to spend a ton of time trying to figure out what the effective nuclear charge is. We do need to understand, though, the difference between outer electrons, or the valence electrons, and the outside, or the valence orbit, and then the core electrons are on the inside. They are going to be completely different, although radius is really just from the center of the nucleus to those valence electrons. Those inner electrons, they have the role of doing what's called shielding, or effectively blocking, absorbing some of the attractive force from the nucleus, because the nucleus is attracting all the electrons, not just the outer ones. We don't notice the radius until that nucleus affects the outside electrons, but it is indeed attracting all the electrons. The more electrons I have in the middle, the more core electrons I have, the more they absorb some of that attractive force. They shield it from the outside electrons. If I take an example here I've got, well, I guess I could have had sodium, but I don't. If I had sodium, which would have my 3 total orbits, 1 electron in the outside, I would have 10 core electrons and 1 outside valence electron. Chlorine has the same 10 shielding electrons, but now has 7 valence electrons. So in terms of the amount of nucleus to valence attraction, 7 electrons in the outside compared to 1. Don't know why I didn't have a sodium up there. Okay, somewhere in your book is this, somewhere online or here. And if you look at this, then almost every atom has 2 different circles to it. One is the atom all by itself, the other is the ion. So what we need to do is kind of focus on one thing at a time, otherwise it gets pretty overwhelming. If I strip it down to just the atomic radius, the neutral atom, the trend looks a little bit like this. And if you start looking your way across the rows, a pattern starts to develop. And if you start going top to bottom, a pattern is there as well. So we want to A, know the pattern, and B, understand or explain the pattern. So we're going to go top to bottom first because it's really simple. Top to bottom, the radius gets larger. Now the main reason for that is we've added a new energy level, but it's got to be more than that. As I add a new energy level that has a higher energy or greater distance away from the nucleus, but also now I've got more what used to be the valence electrons are now core electrons doing the shielding. So more inner electrons shield the outer electrons from that attractive force. So the amount of attractive force reaching those outer electrons or electron is much more diluted or much weaker. So that I've now increased the amount of repulsion, more electrons, and I've effectively decreased the effective nuclear charge, so I've got less overall attraction from the nucleus to the outer electrons. Left to right's a bit trickier because the radius goes down. As the radius goes down, what I'm doing is I'm increasing the amount of nuclear charge. Every time I go one more to the right on the periodic table within a row, I'm adding an electron and a proton, so I'm increasing the amount of things that are attracting to each other, but I'm also not changing the amount of core electrons. So go back to that sodium chlorine example that wasn't quite right. Well, it was right, it just wasn't broken down very well. Both sodium and chlorine had the same amount of shielding electrons, but a different number of valence electrons, and of course a different number of protons in the nucleus. So because the shielding stays the same, as I increase the protons and electrons in the valence, I'm increasing the amount of attraction force without really increasing the amount of electron-electron repulsions. So now the attraction in forces can take over a little bit. So increasing the amount of attraction brings the atom a little bit smaller. You'll see a graph like this. It doesn't really need to worry about it, but I do want you to kind of notice that it goes from the top down, top down. If you were to break it down as to which atoms are doing which, although I think also the noble gases are left off of this, there's a bit of a bigger gap between some of these things. But you'll notice the trend is fairly consistent. There's a few that don't fit the trend perfectly, but overall. Okay, going back to this, there were those other ones. Remember, there was the atoms, but then there was the ions. So we kind of want to focus on the ions a little bit, and I want to caution you right now, the trend with ions is not a left to right, top down, right? We cannot do the same things. And I always give this question because some people think, oh, it's just the same thing. And it's not the same thing. If I look at the yellow circles, those are the atoms. And then I look at the blue circles, and by comparison, those are the ions. They always get smaller, at least going to a positive ion, which I've called up here as a cation, positive ion. So what has happened is I've lost electrons. Now there's two things I can think about this. Number one is for a lot of those I'm losing that entire valence orbit, and what used to be a core and inner orbit is now a valence. But it's more than that, because now I have the same number of protons, positive charge, attracting fewer electrons. I've lost electrons, so I don't have as much electron repulsion, electron-electron repulsion I should say, and I've kind of increased the amount of electron-proton attraction simply because there's a greater force of attraction per electron. There's the same number of protons attracting fewer electrons, so now each electron gets a little bit more attractive force. Point is, they are always going to be smaller than neutral because of that increased attractive force. If I go to the other side, the nonmetal side, where I'm making negative ions, or in this case anions, and by the way, I never really use the term cation or anion outside of this presentation. The green circles are the ions, and the yellow circles are still the neutral atoms. So you notice the green circles are always larger. The reason for that is I'm gaining electrons, which means I'm putting more electrons in, which means I'm increasing the amount of electron-electron repulsion. The other thing is that nucleus has not changed. So where before taking some electrons away meant those same number of protons could attract fewer electrons, now the same number of protons have to try to attract more. Their attractive force is somewhat, I'm going to say, diluted. And of course, the electron-electron repulsion has increased. Okay? So between those two factors, I'm increasing the amount of repulsion, and I'm sort of decreasing the amount of, not necessarily the total amount, but the amount of attractive force that each electron is feeling. That makes the anion, the negative ion, always larger. And we cannot use a left to right argument, even no matter how many times people try. It does not work. Okay, ionization energy, this is where we get to speed up a little bit, and then we just talk about big atoms and small atoms. Ionization energy, as a definition, this is actually quite important, is the energy required to remove an electron. You are probably familiar with this idea that metals like to lose electrons. It still requires effort, it still requires energy to go in to take that electron away. But attractive force then needs to be overcome. If you're going to take an electron away from an atom, that atom is holding on to that electron, maybe not super well, but it's holding on to that electron. There's an attraction there. You have to overcome that. Now, I'm going to say probably obvious that the more an atom holds on to its electron, the more that electron is attracted to the nucleus, the harder it is to pull that electron away. So atoms that have a small radius, attractive force was strong, they are also going to have a high ionization energy. And atoms with a large radius, where the repulsion forces took over more and the electron was way out there because it wasn't being strongly attracted in, those electrons are easier to remove. Those atoms have a smaller ionization energy. And if you were to look at the graph, it doesn't really mean much. You'll notice it's not as good a fit as the radius. There's a few more ups and downs. We don't need to know about that. We want the basic trend, and the basic trend looks the same. If you were to compare it with radius, and I'll do that in a few minutes, it actually fits quite nicely. Okay, top to bottom, ionization energy decreases, and that's just pretty straightforward. Left to right, ionization energy increases. Notice they're different from each other. This is what I was talking about before. As one goes up, the other goes down. Not a perfect fit, but as one goes up, the other one goes down. The electronegativity, this one's a little bit different because it's not a number, it's not a measurement like a radius or an ionization energy. It's more of it's a tendency. It's just well, I'll tell you what it is. It is the tendency of an atom to attract electrons to itself. So you put two atoms in a cage, you throw an electron in, the stronger one wins. It's not really like that, a cage match between atoms over an electron, but that's how it would work. So the ability for an atom to attract an electron to itself depends on a few things. For us, it's going to depend on the nuclear charge, because if you're going to attract an electron, you need to have that attractive force. It also depends on the atomic radius in terms of how close can that incoming electron, get to the nucleus, right? So again, small atoms tend to do this better, large atoms tend to not do it very well. Top to bottom, well, our smaller atoms at the top, larger at the bottom. Then the electronegativity decreases. And left to right, as our atoms get larger, smaller, left to right, our atoms are getting smaller, then our electronegativity increases. They start to attract electrons to themselves much better. And again, the graph, which you don't need to know the graph, I'm never going to show you the graph, I'm never going to ask you to read the graph, but it's not just words, these are the numbers that they have. Okay, there are a few things that we've done. You need to know what the trend is, what it means. You need to know the explanation for the trend, particularly for the radius. The other ones, we basically just said small atoms are like this, big atoms are like that. And then the other one that I'm going to get you to do is the ionic radius. I always ask people to explain that one. Anyway, we'll talk to you in class.